Welcome everyone to our new YouTube video. Please like and subscribe to our channel, help us grow. So today we are going to talk about hierarchical regression analysis, all the mixed effects regression models in R. First of all, we are going to first look at the theory, an introduction to hierarchical regression analysis. So this kind of analysis allows us to analyze data within nested structures, where data points are grouped at multiple levels. So examples of such data include if you are collecting data on students within classrooms, within schools. The students are within the classrooms and the classrooms are within schools. All patients for particular doctors within a hospital. For example, this is an example of a hierarchical structure. First of all, we can have in cross-sectional studies where we have maybe an example of parents and their children. Their children are nested within their families. So in longitudinal structure, maybe we have Eric, Susan, John as subjects J, and maybe you are measuring their weights for a specific period of time, and occasions is I. Occasions are the number of times maybe you are measuring their weight. So that's the kind of nested data we have. So we have this number of occasions. Maybe you are taking weight of these gentlemen and ladies for a period of 6 months, every month for 6 months. So those weights are nested within different measures are nested within each individual. So that's the kind of data we are going to look at. First of all, when you are going to analyze this data, you have to prepare, and like any other data, you have to prepare and clean your data such that you remove the missings or you impute. We shall see that in later videos, how to impute. We can load the necessary libraries, then load our data files, clean and transform the data. It might require you to transform from wide to long or from long to wide. Yeah, that's to make sure that your data is prepared for analysis. Then we go ahead and do some descriptive statistics, maybe the mean and standard deviation, if the outcome is continuous, median and IQR or interquartile ranges, if the outcome is continuous and not normally distributed, or if it's a count. Then we have frequency of counts for categorical variables, and we can have percentages and things like that. So we can also assess for correlation structure at this stage, the kind of correlation underlying our nested observations. There is what we call a spaghetti plot. It is important in visualizing individual profiles over time, as we shall see in how we do it in R. It shows how subjects' responses change over a study period. So an example of code for creating this is using ggplot in R. So we shall see how to do that. So a spaghetti plot is necessary for not aggregating the data for every participant as mean, or aggregating data for an individual over time as a mean. For example, if you are taking blood sugar levels on a participant for like 10 visits, so remember there are spikes and lows and downs and things like that. So it wouldn't make sense if you want to just aggregate the entire blood sugars as mean. So it would be good to see the individual profile, how the spikes all went on for the study visits. So we have histograms and box plots. These enable us to visualize our data, the distributions, and to help us if there are any patterns of outliers and things like that. And now this is a type of regression models that we are going to look at in this video. the GLM, negative binomial, and mixed effect. GLM is generalized. These are generalized linear models. Although we say this data is longitudinal and it's a nested or hierarchical kind of data, so you wouldn't expect us to be even talking about a GLM. But I wanted to show you the difference between a GLM and these other mixed effects models. So in this example, we are going to look at example of patients, TB patients. They were told to cough, although they were given devices that were measuring their coughs every day. So these devices, someone would stay with it for the entire day or for the entire duration of treatment for the first 14 days. And it automatically tallies every time this person coughs. So we want to see the frequency of coughs for the first 2 weeks of treatment for these TB patients. So you see in the GLM, it will consider day was the time, like from day 1 up to day 14. ID was the ID, individual, for the individual study ID. And site, these were 2 study sites. So you see in a GLM, it just considers everything as its own variable without taking care of clustering. The same as with the negative binomial. So we use a negative binomial if there is over dispersion of count data. So we are considering a Poisson model, or what people want to call Poisson, but it's Poisson, because these were counts. The outcome was counts. We are measuring coughs, the frequency of coughs. So we can't have half a cough. So that's why it is a full episode. It's a count. So note that these 2 models do not include random effects. So they don't include the random effects, or they don't take care of the correlation structure or the nested structure of the data. That these are individuals who are represented by IDs nested within study sites, and they are coughing, of which their coughs are also nested within this number of days from day 1 up to day 14. So yeah, that's where we go to mixed effects of models. So this is the mixed effects account for the nested data structure. But we have several types of mixed effects models, so you have to choose the best for your data. And I'm going to take you through this, how to choose the best model for your data. Please note that this is the theoretical model, where this is a lambda ij is the expected count rate of the outcome variable. This is the expected count cough, expected rate of coughs. Beta 0 is an intercept. So beta 1, day 1, we are saying these are fixed terms. So we have the random intercept in this model. That's why we call it a random intercept. It allows to fix the time, and then the rest are random intercepts. So it means that this is the random intercepts for ith site. We are having random intercepts within the individual and the site. So please note that the intercept varies across groups or subjects. So this means that each group or subject has their own baseline level of the response. So it means each group of individual or each participant, they have their own baseline according to the study site and according to that individual. However, the effect of predictors or slopes is assumed to be the same across the groups or subjects. So we see that if we have other predictors like sex, age, educational level, things like that, disease the symptoms of duration of symptoms, it assumes that the rest of the predictors are also fixed. So that's why we can't use this model right now. We shall see. Then we have a random coefficient. So a random coefficient, this would be the ideal model for our study. So a random coefficient model is also called a random slope model. It allows both the intercept and the slope to vary across the groups or subjects. So this is the theoretical model. So the purple, I don't know if this is purple, this is a fixed the fixed term, and the green are the random terms. However, there are two options here of the random coefficient. We either assume that the changes of coughs or frequency of coughs within the individual happens within the individual and within the site. They're independent within the individual and also within the site, and also happens at during a given day. I may repeat that. There are two scenarios here. We either assume that the days have no effect on the coughs, or we can also say that it's only the site and the individuals that have effect on the cough. So where we have the random slope like of the jth site, so the other random effect is the random slope for day within study site, and the other one is the random slope, the random intercept for the ID. So in red, I put for you that baseline count coughs, the intercept varies in both the baseline count coughs and the effect of day across individuals. We shall see where the difference is on the second one. So this one is the random coefficient by ID and time. So for this one, we assume that the effect of cough frequency is due to what happens within the individual themselves, and the effect of time on the cough frequencies. For example, what I mean is, as maybe we go by, as these patients are on treatment, the coughs are expected to go down, the frequency is expected to go down. So that's the effect of time. And the individual themselves, they might be having their own characteristics, maybe the age, the sex, and things like that are making them to have the coughs change. So that's why this would be the best model for this study. However, if we had, for example, if we are giving treatment and we are measuring the effect of treatment over maybe study visits, and we have like 3 study visits, this would be the best model. But since our time is aggregated and we are looking at from day 1 to day 14, and we assume there is a change within days, this is going to be the best model for us. So the baseline cough varies by site. Also, the baseline cough count and rate of change with day vary by individual. Here we assume that each individual might have their own cough frequency per a given day. So we don't say that everyone will have this. This one assumes that everyone will have the same cough frequency for a particular day. So this one assumes that everyone will have a different cough frequency on a different day, and it also varies by an individual. Yes. So model comparisons and results. We do model comparisons using AIC and BIC. So AIC and BIC and residual plots. AIC and BIC is good for always done in the models that have likelihood ratio tests or likelihoods. that are run through likelihood. So we compare AIC and BIC, and we choose the one with the least AIC and BIC. So we examine also residual plots for model assumptions that we can see. And finally, we pick the best fitting model, as we are going to see. So thank you. Let's run straight to R and we see what we were talking about. First of all, we are going to set our working directory and remove everything from the environment. So environment is clean, and we set our working directory. So let's load our data. We shall be using data long. It is in the long format. Let's view our data and see. So we have studied sites. There are 2 study sites. We have weeks on treatment, the gender, HIV status, smoking, DM, age, and things like that. Then we have cough frequencies on day 1, cough frequency on day 2, up to day 14, the first 2 weeks. So we go ahead and load the different libraries. These are a lot of libraries. I put them here such that you know where they work, but we are not going to use everything here. Yeah, so I just put some just for you. If you want this code, I will put for you a link where you can download it, or I will upload it on the R blog website. So we have this one's for data labeling, summary statistics, but the most important libraries are this one for the linear mixed effects model, this one to test the linear mixed effects models. We have the GEEPAC or generalized estimating equations. We shall see why we can't use generalized estimating equations for this case. Then we have GE effects for marginal effects. We have tidyverse. You know tidyverse is used for data manipulation visuals. It has the ggplot and the deep layer. We have the theme packs. Haven is for reading stata files. So the rest are for changing around themes. So since we have already loaded our data, let's read the columns. We have this simple data set. We have the ID, study site, HIV status. Day is from day 1 up to day 14. Cough day is the cough frequency. Those are our main variables. So we can start by looking at our main variables. So I would also include data structure here, and such that you see the structure of our data here. So put data structure. I have put df is equal to data long because I want to be manipulating df while leaving our initial data or the main data frame untouched. So if we look at the structure of our data, we see that IDs is numerical, yet this is in this study we consider each individual as their own because data is taken for throughout 14 days on the same individual. So this individual becomes their own control. So it has to be categorical. These are number of days 1 to 14 has to be, we shall see when to be categorical and when to be numerical. Study ID, this is same as ID and study ID. So study site, we have 2 sites. That's the cluster we have. And maybe the other thing is cough day, which is numeric. That's okay. So we can also see which one is a character, which one is a double, and things like that. So we are going to record our data and we rename the days from day 1 to 14 and make it as a factor or categorical, and the rest of the data as numeric and categorical as deemed necessary. So let's start by summarizing the outcome, that is the time periods. So let's summarize we summarize by we get summary statistics, summarize by day. Day is the number of days from day 1 to 14. You see cough day, I said these are the cough frequencies. There are 100 patients. Minimum on day 1 is 3, maximum there are 4 cough frequency. 720 frequency was the maximum on day 1. On day 2, minimum 0. This is for all the participants. So we have the median, the interquartile range, so the mean, standard deviation, and things like that. So you can know what's going on really by looking at just the medians, and you see that they are going down. So another thing, let's look at the pairwise correlation matrix. So okay, all right, what did I do? Oh yeah, first we have to change the data from long. We had long as we have where is our DF? This is our DF. So we had data, oh my god, from their data long. Yeah, let's use this and we see. Okay, we had the cough day, which was summarized into cough day and day, which was summarized into day was the day 5, 4, 3, and the cough day was the frequency for that day for every participant. That for each participant, that's the longitudinal type. So let's look at I hope I haven't closed what we are looking at. So let's look at the wide format. So the wide format is this separating the days, day 1, 2, 3, 4, and each with its own cough frequency. We want to look at the frequency, the correlation structure between these days. If there is correlation between these days, we conclude that this data is correlated data, and day 1, the frequency of day 2 is influenced by frequency of day 1, frequency of day 3 is influenced by the frequency we got on day 2, and so on and so forth. So let's return back to our code. So let's look at the correlation matrix. So this is the correlation matrix. We see day 1 and day 1, that's supposed to be 1. Day 2 and day 1, 0.75. You see there is a very high correlation between this data. So this data is highly correlated. It means the cough frequencies of day 4 are related to cough frequencies of day 1, day 2, and day 3, and so on and so forth. So we can also visualize the cough frequencies by using the reshape tool. So we can use the correlation heat map. This is the scale where you see this yellow or orange. I think it's yellow. The correlation is almost 1, and you see here it's almost 1. So you see that the correlation between days is so much, and this is the time effect, the correlation of coughs within days. So let's also, we can visualize using we can choose a few columns, like from day 1 to day 4, just to demonstrate this correlation. So you see that is a high correlation, as you can see from even the scatter plots, and you see even the correlation coefficient is high. So we can do the correlation per site, and we also visualize correlation per site. We look at there are 2 sites, Kisenyi and Mulago. There is even high correlations between the 2 sites. It means the also sites have a correlation structure, they are correlated. So let's also go ahead and look at the summary statistics for our outcome. So in order to see if this outcome is normally distributed, we can look at the mean and the standard deviation, and also we can look at the median and interquartile ranges. For normally distributed data, the mean is equal to the median, or almost equal to the median. And we can see here, nope, not even close. and the standard deviation is so wide. So it means that our outcome is not normally distributed. But no problem, since it is a count, and more and Poisson takes care of this kind of over dispersion. So let's look at the spaghetti plot, the individual profiles of our participants. These are now coughs against the days. So you see, like for this individual up here, the curve started low, went up, went down, and something like that. So you see there are some spikes. This is what we call a spaghetti plot. It looks like spaghetti. So this is for individuals. You know it can give you an idea of what's going on per individual. So we can look at also the individual profiles per study site, where this color is it red? Is this gray? Is Kisenyi, and the other one is Mulago. You see that these people of Kisenyi had high cough frequencies compared to those of Mulago. Then we can visualize using a histogram. We are still visualizing our data. We are visualizing the outcome. First of all, a normal histogram, you see that data is madly skewed to the left. And when we add the frequency and the K density, you can see so skewed. But don't worry, Poisson regression takes care of that. It knows. So if we go ahead and we do by site, you can see this is Kisenyi, this is Mulago. You see the differences in the distribution of cough frequencies. We saw that Kisenyi is a bit higher as we go for some individuals. So we can also visualize the distribution of coughs per study using box plots. Although there are several, this dot is a mean, the middle bar is the median, and these are interquartile ranges, and these are considered like these are the whiskers, and these can be outliers. You see that the data, since it's so skewed, the box plots are so narrow, with showing several kinds of outliers. So let's visualize the distribution of cough per time period using box plots. So what happened to the cough plot? The coughs per day. So you see the dot is the mean. You see that the mean went up and slightly reduced. Even the middle bar is the median. You see the median slightly went down. So this gives you an idea what happens. So we can look at this per site. Tells you still Kisenyi had higher interquartile ranges and higher medians. The blue dot is the mean, as you can see. So let's visualize the mean coughs by a time period. So although in this kind of data, since it's so skewed and it is individual profiles and each patient has their own profile, using mean plots don't make much sense, but still they give you an idea of what is happening. So you see that the cough slight decline as the cough frequencies decline as time goes on. You can do this per study site. You see Kisenyi is always on top. People had a mad cough in Kisenyi compared to those in Mulago. So we can, since it is non-normally distributed, we can also try to use median and interquartile ranges. You see there are very wide interquartile ranges, and these dots are the median. Also the medians go down. The median plot is kind of close to reality when it comes to skewed data. So you can do median plots per site. You can see they come and cross, but still Kisenyi had wide interquartile ranges and medians here. So let's visualize cough by age and site. We can also do that, and we see what happened for people who were old, and what happened as people ages advance versus the coughs they were producing per day. As you can see, the old ones in Mulago, although they were giving coughs below 500, you see the highest number of coughs are those guys below 35 years old. So the highest number of coughs is up, given by young people below actually 25 years. Yeah. So this is just to visualize your data and to give you what is happening. So if you want to analyze this data using OSO, you can still, because it is madly skewed and over dispersed, but still we can transform that outcome into a log or a natural log, and we see if it will make our outcome normally distributed. So let's do it by only including the finite variables, the finite figures. As you can see, it tends to become a normal distribution, although it still has that skewness, but if we remove the outliers, you can see that it can come into a normal distribution. This is a log transformation. And if we go ahead and look at the mean and the median, they are close to each other and the standard deviation is low. So interpretation of such data can be slightly hard because you are using logs. This is now log cough frequency instead of the cough frequencies. So we can go ahead and do a spaghetti plot for these profiles using the log coughs versus time. You see how it has changed. Yeah, we can still see. Now we can add a trend line. So this trend line, you do a scatter plot of frequency, the log cough frequency versus time, and you include a smooth line to show the trend. So you see it is slightly declining as time goes on. So we can also do histograms basing on the site, and we see I can also add the normal and the cadence. You see Mulago is slightly normally distributed. It is Kisenyi which is a bit skewed. So this helps if you want to analyze that as a normal distribution, or as because it ceases to be a count, now it becomes a continuous variable, and we can use, instead of using a POSO, you can go ahead and use the data from you can use models for continuous variables. Yeah, but box plots, we can go ahead and look at them for the log transformed. This is the mean for the log coughs, still goes down. The medians, this is the mean between two, still gives the same. The medians still has high interquartile ranges. Let's go ahead and see the medians. So don't worry, we are going to look at the regression analysis. We can also look at the scatter plot. Now you can see that the scatter plot for log coughs, it still gives the same interpretation. The young ones have higher log coughs compared to the old ones, but slightly between them. It's in between the middle, between 2 and 6. So now